class, we're going to cover 2.5 and 2.6 today, which is zeros, polynomial functions, and rational functions. Now, rational functions will primarily be about graphing them, talking about asymptotes, but zeros and polynomial functions will be most of the time we spend today. So if you have any questions about how we do that, please make sure to write down the questions so that we can fill in the class. Now, first thing we're going to do is actually fill in these notes. So we're going to fill in the notes concerning the definitions. And we have quite a few. And then after we fill in basically till this point, upper and lower drawing, we're going to go into the same process. Okay. So the first video will be definitions, second video will be examples. So if you need time, at the end of the video, I will go through it so you can pause and write down stuff that I covered. Okay, so the fundamental theorem of algebra is actually about finding zeros. So if f of x is a polynomial, of degree n. Now this is a crucial definition, so please make sure you're of degree n. What's the definition of x? Degree n? Oh. That's interesting. Okay. Of degree n, where n has to be greater than 0, then function f has at least 1 0 in the complex numbers. Sorry. In the complex number system. Okay? So remember, complex number system, this is going to be where it's a plus or minus bi. Okay. Now, so if it is a polynomial of degree n, so n is a number greater than 0, polynomial means powers have to be integers, positive integers, so 1, 2, 3, 4. It has to have 1 0 in the complex number system. This is just okay. Linear factorization if, again, f of x is a polynomial of degree n, and where, again, we're going to be seeing much of the same things. N is going to be greater than 0, same concept. Then f has precisely n linear factors. As n linear factors, where we're going to write this out, where we can write f of x equal to a x minus c1 x minus c2 x minus cn. Okay, so we'll have linear factors that way, where c1, c2, cn are all going to be complex numbers. Okay? Again, remember complex numbers, a plus bi. Let's actually, there we go. Okay? Rational zero types. Okay, so this is our first two definitions. This first one is telling us that there will always be one complex number that is our 0, and the second one tells us that there's linear factorization. up to x minus c1, x minus c2, so on. Remember, this is from when we did synthetic division. Same idea, same thing. Okay? Rational zero test. If polynomial, now this can actually take a little while. So f of x equals a sub n of x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a sub 2 x to the 2 plus a sub 1 x plus a sub e. Okay, has, it's going to be integer coefficient. So if this function, polynomial, has an integer coefficient, every rational zero of f has the form rational 0 equals p over q. Okay, rational 0 equals p over q, where p and q have no common factors other than 1. So they have to be two different things. And p is going to be a factor of the constant term a sub 0. So p is divided by q, so p is the factors of a0, and q is a factor of the constant of the leading coefficient. So you always divide the factors of the constant term by the factors of the leading coefficient, okay, to find rational zeros, okay? So this is our rational zero test. Conjugates, remember, this is just really simply put. This is if we have a plus bi, the conjugate is a minus bi. Okay. Okay, let's look at this definition. We're going to get through these. We got 2 more minutes, so let's go through this pretty quick. This let f of x be a polynomial function. Polynomial function that has real coefficients. Polynomial that has real coefficients. So it shouldn't have imaginary. If a plus bi, where b is not 0, so b is a 0 of the function. Okay, so if we got a complex 0, the conjugate, that is a minus bi, is also a 0 of the function. Okay, so if a plus bi is 0 of the function, a minus bi is going to be 0 of the function. Okay, that's complex. That means they always come in pairs. Okay, they always come in pairs. Okay, partial of signs. There's back to polynomials. we're going to fix that. Okay. Let, actually, f of x equal a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, plus dot dot dot, plus a sub 2, x to the 2, plus a sub x, plus a sub 0. Okay, let that be our function, be a polynomial with real coefficients and a sub is not equal, a is not equal, sorry, a sub 0 is not equal to 0. Okay. As long as that's true, the number of positive real zeros of f is either equal to the number of variations in sign of f of x, or less than that number by an even integer. Okay? So that if the positive real zeros will either be equal to the number of variations in sign of f of x or less than by an even number. The number of negative real zeros of f is either equal to the number of variations in sign of f of negative x, or less than that number by an even integer. Okay, so they're both by even integers. We'll talk about this in a bit, okay? Okay, upper and lower bound, this will be the last thing we do, and we'll, actually, you know what? I think we'll come back to this later.